Live have started. Okay. Welcome everyone. Welcome to the seventh day of Open Science Labs Quantum Computing in an Axel lecture series. In the past lecture, in the sixth lecture, we have discussed about some quantum circuit pipelines and some other basic codes which we can do with QIS Kit and some other frameworks. Today we are going to discuss about the quantum AI with also examples, real world quantum simulations. Uh, we are going to discuss today. First of all, I welcome everyone to this session. Basically, from the beginning, we have discussed various topics in terms of quantum mechanics, bio-quantum physics, and some other mathematical methods. Also, we have discussed about the QIS kit, the fundamentals of QIS kit, also some other codes. Maybe some people feel like they couldn't be able to understand some of the frameworks and some of the things which I'm going to explain today. But don't worry about those things because if you go to a LLM model, maybe Gemini or ChatGPT, you can get most of the information from it. You can easily get explanations for those some of the complex mathematical functions. Also, you can interrupt directly on this meet. I will give my answer as much as possible. And if you have any doubts going further, we can have a special session maybe in the next week to solve those doubts. For brief, I'm going to give an introduction about artificial intelligence. We already know that artificial intelligence is nothing but an machine model or something like a mathematical function which can able to understand the human data inputs and try to manipulate those inputs. Like I'm saying, I'm counting from 1 to 10. The artificial intelligence model also tries to count from 1 to 10, and we applied a ton of frameworks to that, like transformers and linear regression, from linear regression to transformers, and we finally ended up being created a so-called LLMs nowadays, and we can do almost everything in the present day, like writing code and getting information, getting your work done with AI. But the true purpose of AI would be in the form of quantum computers. The quantum AI would be able to create way more innovations than we are having right now. Quantum AI is a really fascinating field, but currently we don't have access to those kind of quantum computers. So basically, what we are going to do is we are going to simulate those quantum computers using PyTorch as well as PennyLab. For newcomers and people who don't know about these kind of frameworks, I will give a brief about PyTorch. PyTorch is a easiest framework which is available in open source. It is a linear regression and a polynomial regression model. Basically, PyTorch is the basic fundamental for most of the LLMs which we are using right now. There is way more other frameworks are there, but for my code, I'm currently using PyTorch. PyTorch is nothing but it is just predicting those next lines or next numbers or next values like that. That what we are currently doing with our LLMs. Like if you go to ChatGPT or Gemini and write me a letter or maybe a poem or maybe a story for me, it is just predicting the next word and doing something great. And there are tons of internal things associated with machine learning and deep learning and some other topics. But currently, for quantum analysis, in the field, there is a major problem in the quantum computing. Like according to quantum theory, we can't be able to recreate an identical wave. According to quantum physics, let me imagine a particle which is propagating on the space, maybe an electron or maybe a proton or maybe something else, maybe calcium atom or a carbon atom. We can't recreate the exact waveform again. Like inside a chaotic situation or maybe inside a cell, we are having a ton of atoms. Like currently we are having 1,000 atoms or 2,000 atoms. We are calling them as qubits. Uh, they all oscillate together and they create waveforms from out of it. One second, I will explain in the board. Okay, I think I can explain here very well. I hope you can see this. Let me consider this as a wave. Maybe this as a wave. Okay. Let me give you a straight view for everyone. Okay. Now everything is fine. Basically, it's just a wave which is propagating right here. Let me imagine a quantum circuit. Okay, if you have any doubt, you can ask. Maybe if you are in mute, you can ask in the chat also. Giri. Or we can continue the session. If you have any doubt, you can ask in the chat box. Also, you can unmute. If possible, you can unmute and ask directly. Or otherwise, I will continue. I think we are having around 10,000 or maybe atoms here. Each atom oscillates on its own, like it is rotating on its own, and it is creating a waveform. Finally, at the end product, we are getting a very complex wave. Each and every time we are getting a ton of complex waves. We can't back propagate those waves in quantum theory. So in theory, we can't be able to recreate those waves. So there's something like if we send the information, that is okay, but we can't regenerate it. In classical computers, we can generate any kind of data. Okay. In classical computers, we can regenerate those data, but in quantum mechanics, we have a term called wave function collapse. So we can't be able to regenerate those informations. So in terms of quantum AI, from here, what I'm trying to solve is I am going to create a framework which can be able to do this back propagation, or maybe which can be able to reduce the stuff with wave function collapse, or maybe it is just trying to manipulate those values and trying to predict those values using for here we are using three major libraries here. We are using SciPy and NumPy for array manipulation and some other stuff. We are using PyTorch for machine learning, and we are using Penguin. Penguin is also a quantum circuit based framework, or maybe quantum library, which can also be used to do some extraordinary things. So we are using these three frameworks to work, and we are going to trying to predict those values. So what we are currently doing here, first of all, I hope my screen is visible right now. I will share my project here. I hope you can see something in the screen. Maybe some people may think like, what is this? Something like a ECG machine or something else. Maybe present in the intensive care units, or maybe from my right side there is a term called wave function collapse, and it is like booting some audio signals and stuff. And there is also an blue dotted lines representing something else. What is that? Let me explain this one by one here. First of all, here what we are doing is we are getting an input from a LED, and we are using legendary wave reconstruction formulas to reconstruct these waves using machine learning. We are using active machine learning tools to recreate those waves. We are just recreating those real world data using machine learning, and we are feeding them to a quantum computer. and trying to reduce those wave function collapses. Like what we are basically doing is we are feeding the information to the quantum computers. It is encoding and decoding the information, and we are comparing this information with the machine learning information. Maybe you get confused with this. Let me reveal the quantum computer, the low budget quantum computer which I am having right now. I hope. 1 second. Let me share this. I hope my screen is visible to everyone. 1 second. Okay. This is the low budget quantum computer which I am having right now in my hands. Maybe it is an Arduino Uno board. Maybe the camera angle is not so visible for everyone. And that small LED bulb. Small LED and a small Arduino Uno board. That's all what I'm having right now here on my hands. From using this, what I am really doing is I am just getting some raw data using this LED. Right here, you can see this is the LED right here. I hope the screen is visible to everyone. Let me jump to my program here. You can see you are getting value, and let me touch this LED again and again. You can see there is a variations in the output. You can see the variations. Basically, the light emitting diode, what you call it as a small LED or a light emitting diode, is also a sensor, which is also a sensor, which can also detect the real world data. Like in quantum world, I am living in a quantum. Everybody is living in a quantum world where photons are propagating here and there everywhere, and particles are propagating over there. If a photon hits on this tiny little membrane which is present inside the LED, we get some input from here. We are reading those inputs using Arduino Uno board. I think I don't have any another board here. Maybe this is visible on your screen. This is the Arduino Uno board. You can purchase for around $5 in India. And what we are doing is, let me explain. We are having a Arduino program here, which is kind of similar to C++. We are getting the input data from here. We are getting analog input data. We are getting this data every 20 milliseconds once. We are getting this data with around 9,600 bits per second. This is the accuracy we are getting right now. From this data, what we are doing is, this is the real data. The green ones are raw LED real world data which we are getting right now. And these dotted lines are the true thing behind the quantum machine learning. We are using Legendre framework to recreate those waves. It is just recreating the real world pattern. We are just fitting the real world information to a machine learning model. We are just explaining real world data to a machine learning model right here. Like this is just a LED. If I put my watch over here on the LED, you can surely see the values get peaked. There is a various amount of change in the value. It gets to the high state. If I remove it, the value suddenly gets changed into the waveform. That is what I am currently doing right now is I'm considering this LED as a quantum computer, as a quantum detector. It is detecting those incident photons or the real world data. I am considering this real world data as qubits and manipulating them and trying to find those ways of this stuff, what you call it as this raw data. I'm fitting this into a particular machine learning model, maybe made by PyTorch, and I'm fitting this information directly into the quantum circuit which is developed by Pennyland and getting some information, and I'm trying to find how I able to reduce the wave function collapse here. Because wave function collapse means the entire information is lost. We can't be able to restore the information. If there is a tiny amount of power cut which happened in your quantum computer, your entire information will get be lost. That is the thing. What is going on with quantum computers? Basically, if power cut happens on your desktop or PC, if you are typing something, the information will get lost. If you don't save the file, or if you don't use internet, or maybe if you don't use cloud-based environments, you will lose the entire information in the classical computer. But there is a possible way to retrieve those information. But in quantum world, we are just studying a particular wave which is propagating inside a chip. If we lost something here, how can be able to decode the information? It may sound like simple, but in the real world, it will create. Maybe now I'm audible. One second. Okay. Maybe there is a network issue there. We'll do something. Sorry, one second. Once again, I will join on other device also. Maybe network issue. Okay, I hope now I'm audible. I hope now I'm audible. I think so. One second. Let me start from the beginning. Uh, yes. Okay. Thank you. What is basically we are doing here is we are predicting the real world information, and we are fitting it into a machine learning model and trying to find the pattern of the information, and we are currently trying to predict the information here. That is what we are currently doing. Is it may create some confusion to some other people, uh, but I will explain with the code itself. First of all, let me share my screen once again. I hope my screen is visible to everyone. I think so. What we are getting is, it is a real world information. It is a real world LED data which we are getting right now here. Real world LED data, and this legendary wave reconstruction. These blue dotted lines are reconstructing the information, and it is predicting the information, which we are using as a safeguard to handle the wave function collapse. Maybe there is a collapse may happen inside the data, uh, inside the computational field. We will lost all the information. Like we had faced a network issue right now. You lost some of the information in between that. But in quantum computers, if I lost this in between information, you will lose the entire information. That is the main issue with quantum computers. That is the main thing. We have to be way more careful about quantum computers. So what we are doing is, we are using machine learning. That is my own very own model I am using right now here. Like, I am just trying my own self to reduce those wave function collapse. You wouldn't be able to find this technique in any other research paper. I'm doing this on my own, but there's a ton of frameworks. Other frameworks are there. Maybe they are efficient, way more efficient.
But what I'm explaining here is we are able to reconstruct those informations with a very low loss, very low collapse, maybe. Like we are reconstructing those information without that much of loss here. Let me reveal the code once again. This is the code here, which can be named as physics informed quantum auto encoder and quantum state reverser, which is published under MIT license. Uh, Permission hereby granted. You can share with anybody who you want. We are basically using some other libraries here, maybe the serial and time for getting the information. We are using NumPy for our calculations, basic array calculations. We are calling PyTorch neural networks here. We are using PennyLAN QML here, and we are using SciPy special legender functions here. We are also using Matplotlib for this wonderful graphical representations here in the screen. What we are basically doing, we have created a circuit using 8-point legender. We are having a 8-point legender value here. We are having a 3-layer quantum circuit. We are using 4 qubits here for this thing. We have a particular learning rate here. I will explain it later. Classical pre-processing, we are getting the information. We are changing the informations using legendre polynomials. Basically, what does it mean by legendre polynomial? Why we are using this legendre polynomial here? That means that most of the days, there is information. This particular LED stuff can get a data from 1 to 1023. That is the electronic value for this particular small light emitting diode. What we are doing is we are converting this information in between the range of -1 to +1 for our convenience, and also we are removing those unnecessary stuff. Like we are getting a ton of inputs over there. We are removing those unnecessary stuff, and we are just getting those particular values, particular MLFET values, because we are running a real world quantum circuit, real world data circuit. Even my computer wouldn't withstand those stuff. If you are fetching those information, like it will stretch from 800 to 0 and so on, so that will create a mess. So we are using this legendre polynomial for better efficiency. We are using this, and what we are doing is we are currently here. We created a This is the layer. And the third layer is the physics layer. We are using kg operators, like how does the momentum, how does the mass. We are just manipulating those atoms here. This is some of the manipulating parts. Like we are using CG couplings, which are known as CG coefficients, Klebsch-Gordan coefficients here. If you learn very deep in terms of quantum mechanics, you will find those angular momentum operators in terms of quantum mechanics, where you can find those basic understanding about how does the eigenvalue spectrum and some other stuff are doing work in the quantum mechanics. So these are some complex quantum mechanical functions I am using here. And for here and afterwards, we are successfully created our advanced quantum circuit here in the line, and we are calling this as a function, as a decorator function here. And this is our quantum reversal circuit. We are building a Hadamard gate, which is also an quantum gate format. We have CNOT, Hadamard, and some other gates are there. We will explain later on the lecture series. And here what we are doing is we are fitting those legendre polynomial informations to the uh, quantum circuit and try to decode the information again, which returns the probabilities here. We are just returning those probabilities, and these stuff are just for the dashboard. These things doesn't have any that much of weight here. And where is the main part? I have to find it. 16 dimensional quantum. Here. And what we are making is we are we initialize the neural network for the legend is 8. Number of legend points are 8. But here we are converting them into a 16-dimensional quantum space by zero batting the higher order states to create a target distribution. Basically, what we are doing is here we are converting this 8 dot information. Let me imagine like this legend waveform is the 8 dotted information. We are converting this into a 16 padded information. We are fitting this information and getting this as an output. You can see almost these things gets from 0 to almost 0.5. This is the last which we are getting right now here in this. Like we are basically reconstructing those waves here in the circuit itself. We are reconstructing those waves and we are trying to find, basically we are trying to, let me get it once again. Yes, basically we are fitting the real world data to a legendary point or a machine learning program, and we are fitting them into Pennyland quantum circuit, and we are then encoding the information. Yes, sir, you can ask your doubt right in between that.
So what you are essentially done in a very plain terms is you have converted something from an 8 bit information into a 16-bit information, and you reduce the loss using the legender function. Is that's what you are accomplishing there?
Well, not like that exactly. We are convert the information. Basically, this 8-bit legendary stuff is um, like, how can I explain? We are fed to a machine learning system, and we converted it to a 8 daughter line. That's all. But then when we fed this information into a quantum circuit, it reads the information and it gives a yielded output. And we are comparing the input and the output simultaneously. We are comparing the input and the output simultaneously, and we have reduced the loss here
Okay.
in this
Okay.
way.
So it's basically an
Basically,
input and an output, but you did not
yes, yes,
extrapolate that information. Okay. Thank you.
yes, yes. Here is the application. Now only I got it. Here is the application is uh, in the real world, we are fitting the real world wave information. Maybe if it the information which we are getting from a quantum chip or something else, we are directly fitting the information into the quantum framework or maybe program or something else. We will, if we didn't be able to uh, save the information, or maybe there is an environmental hazard or maybe any environmental loss, we will lose the entire information. But what we are currently doing is we are doing a machine learning program. We are doing a machine learning code here, and we are fitting the information to the machine learning layer. We are getting a machine learning output. We are fitting the output to the quantum computer, and we are getting a manipulated somewhat some we are fitting the legend output as an input to the quantum computer, and we are getting a 16 bit output from the quantum circuit itself. We are comparing the information simultaneously. We are comparing the information with the real world or maybe the machine learned information, and we came to a end. We came to a conclusion that we would able to uh, like, I hope you can understand, we will able to solve the problem of wave function collapse here. Maybe we already machine learned the information, or we already registered the information, and we giving it to a quantum circuit. So there is a possibility that we can retrieve our information, even though there is a physical loss in the network or maybe environmental hazard happened inside the quantum chip. We can retrieve our information. That is what I'm currently done with a quantum AI. I am currently done with this quantum machine learning program. Or maybe in the real world, we can do quantum AI stuff like advanced LLM or something else. But here, my problem statement is how I am able to solve this thing. How I am able to solve the wave function collapse problem, which is a real hazard we are facing quantum, in terms of the development of quantum computers.
Thank you.
Okay. I hope I have done so far for this today's class. One second. Okay. I hope others also may get a basic idea regarding this thing. Can we move on to our discussion session? Let me just turn off the live from now here. For those people who are watching this recorded session on YouTube, this lecture series will happen every week Saturday. Uh, every week Saturday, uh, 10:15 p.m. IST, Indian Standard Time. We are doing this as a community-driven project under the help of Open Science Labs, which is an international open source organization focused on open science and open technologies. And I will share this information I will share this code on my GitHub repository as soon as possible. And if you want to join our discussions formally, you can join. You can visit our website uh, and blog information. I will share here. You can go to Google and search for Open Science Labs. You can directly search for Open Science Lab. You may get the first link here for the Open Science Labs. Uh, when you go to the partnership session, you will find the community partners here, and you will find my information. We are taking this quantum computing in a nutshell lecture series. This is our 7th week. It is a weekly online lecture series and discussions. It is entirely focused on audience of students, researchers, developers, educators, and science enthusiasts worldwide. And currently, we are trying to get more affiliation from people all around the world, like American Physical Society and some other reputed physical organizations all around the world. We are trying to get some affiliation, and we are getting some good amount of response over there also. It is an entirely community driven non-profit initiative. You can find the exact lecture link. The link will be the same for every day. This meet.jit.c OSL quantum lectures, and you will find the more details here in my blog website. You can click here and you will find all the brochures and posters informations over here, and you can join my Discord channel, so you can have some information and discussions over there. And I have a plan to add more books and study materials on my page, and we will have a very quality amount of discussion in the future. And for those people who are thinking like, oh, what I have done here right now is I have used my own ideology to develop a quantum AI, maybe a basic amount of quantum AI, or maybe a quantum machine learning. I just combine the machine learning to safeguard my information. I'm just trying a new layer to safeguard my information, um, because I will lose my information if there is a wave function collapse. So I tried a new stuff here. On the upcoming sessions, we will also going to see way more advanced quantum circuits in the future. It is a community-driven project. We are just expecting your support. Thank you for watching this video. Afterwards, for the people who are joined here, don't leave this session. We will have discussions after end of the live session. For the people who are watching this YouTube live or recorded session, that session will be end from here. Thank you for